Hello, ladies and gentlemen. My name is Agita Vivi. In this occasion, I will present my and my colleague's research about preliminary verification for subseasonal to seasonal precipitation model on 4 specific conditions over Western Indonesia. This is the outline of my presentation. The first one is introduction, and then data and method, result and discussion, conclusion, and references. We know that there are several weather and climate phenomena detected around the world. Those are INSO, KBO, PDO, equatorial waves, and so on. Indonesia is located around the tropics, and some of the most well-known phenomena around the tropics is Madden-Julian Oscillation or MJO. Besides MJO, Indonesia is also affected by northerly cold surge or NCS. These two phenomena will eventually increase precipitation over Indonesia and even lead to extreme precipitation. Due to preventive action for the extreme precipitation, we need an advanced forecasting model which provides a longer lead time. The subseasonal to seasonal forecasting models, as a bridge between conventional and seasonal forecasts, provide a longer lead time, up to 60 days ahead. Just imagine we can detect extreme rainfall 2 months before, when the preparation can be made and the damage can be significantly reduced. The utilization of S2S forecasts on the prediction and simulation of MJO as well as extreme events show relatively good results. However, research concerning verification or validation of the models over Indonesia is hardly to be found. Therefore, the ability of the models needs to be investigated over the area. More detailed analysis is conducted on 4 specific conditions with monthly analysis in November, December, January, and February, analysis when only MJO active, only NCS active, and when MJO as well as NCS active at the same time, where extreme precipitation are likely to happen. This is the data and method. About 4,000 ground rainfall observation points over Sumatra, Java, and Kalimantan with 20 years data are quality controlled using cross-check error and removing data with zero value for more than 100 days. 645 points with data availability more than 70% are then used further in this analysis. The S2S reforecast precipitation model from ICMWF with a real-time date of the whole 2008 was then extracted for each point and each time step. We used the control and the first member of PERTSET model with 3 earliest and 3 latest time steps to provide a better comparison. The ground observation and S2S precipitation forecasts were going through statistical analysis by calculating the distribution parameters, rainy day fractions, correlation coefficient, RMSE, and so on. Next, we use RMM index and mean sea level pressure gradient between Kushi and Hong Kong, as well as meridional wind from reanalysis dataset to identify the MJO and NCS active days based on some specific criteria. The next step is conducting composite analysis to describe the similarity between observation and S2S precipitation forecasts. Now, we are entering the result of the study. The picture shows gamma distribution parameters including shape, scale, and location of observed and S2S model precipitation for both control and perturbed model in the first and last 3 time steps. Perturbed model in its first 3 time steps shows superior result for shape parameter, especially around Kalimantan and some points over Sumatra, as well as in location parameters for the whole observation points. Next is the picture of rainy days fraction for observation and models. The models seem to have rainy days fraction far higher than the observation data, which ranges from 13 until 81%, while the forecast ranges from 49 until 99%, showing the tendency of S2S model to forecast non-rainy condition as rain. Next, there is a 2 set of pictures. The picture in the upper left shows histogram for 6 points throughout the study area. Those are North Sumatra, Riau Islands, Bengkulu, West Java, East Java, and West Kalimantan. In those points, S2S models forecast rainfall with intensity between 0 to 5 mm per day, far below the observation. Meanwhile, in the higher rainfall intensity, the models tend to overestimate the forecast. The lower right picture shows scatter plot between observation in x-axis and models in y-axis. No linear relationship can be concluded from both datasets for all 6 observation points. The pattern indicates that the models tend to underestimate high rainfall intensity and overestimate the low. This is the correlation coefficient and RMSE for daily and vented accumulated precipitation, as shown in the box plot in the upper left figure. From the correlation coefficient and RMSE, we can see that the first 3 time steps perform better than the last 3 time steps, both in daily or vented accumulated precipitation dataset. Another thing is that the control model has slightly better performance than the control model. The spatial mapping of correlation coefficient shaded and RMSE represented by the circle size of daily and vented accumulation precipitation with minimum confidence level 95% is shown in the right figure. Lower figures show points with correlation coefficient higher than 0.4. In line with the box plot, the first 3 time steps show higher relation with highest daily correlation coefficient found in Natuna, while independent accumulation is found in Rio. Next is the spatial analysis. The long-term daily average of observed and S2S precipitation forecast for the first 3 time steps for the periods of November, December, January, and February. Number of days average is shown at the top right of each map. There is no significant difference in the precipitation forecast by the control and perturbed S2S models. Both models provide similar precipitation pattern, with values would be lower in the control or perturbed model. This is still the same picture, but when MGO is active. The S2S model is unable to correctly display the spatial variation in each observation points, mainly due to the resolution, but it can recognize the wet and dry phases brought by the MGO. The wet phase in phase 1 until 4 and the dry phases in phase 5 until 8. Still the same picture, but in the day when only NCS active, 3 days before up to 3 days after NCS reached 15 degrees north. No significant difference in precipitation pattern is detected over the study area. In the observation data, the increase in precipitation began to be seen at T+1 and consistent up to T+3 around Riau Islands and West Kalimantan, but it could not be clearly observed in the model. This is the long-term mean of precipitation 1 day up to 3 days after NCS reaches 15 degrees north on every MGO phases, which are accumulated to analyze the performance of S2S models to forecast the effect of the interaction between MGO and NCS on the precipitation over the study area. The models are able to catch the pattern but hardly predict high and low intensity due to MGO and NCS correctly. From the result, we can conclude 4 things. Those are: performance of the S2S control and perturbed precipitation forecast over Western Indonesia varies on the location and corresponding condition. The perturbed S2S model show better performance in the statistical comparison, but the correlation coefficient and RMSE is slightly under the control model. Both models can catch the precipitation pattern and variation brought by the wet season in NDGF period by the MGO and hardly show a hint of NCS effect. And the last one is that the S2S models is hardly predict the value of high and low precipitation, thus it tends to overestimate low rainfall intensity and underestimate the high one. I would like to thanks to European Center for Medium Range Weather Forecast for the subseasonal to seasonal model precipitation dataset and Agency for Meteorology, Climatology and Geophysics for the ground observation precipitation dataset, as well as the Center of Education and Training of Agency Meteorology, Climatology and Geophysics for the scholarship at Applied Climatology IPB University. This is the references used for the research. And that was my presentation. Feel free to contact me if you have any question. Thank you very much.